single Novartis or roads, it's possible to get different colors. But these different colors means that you have an absorption at one specific level. And if you can imagine to display these nanoparticles very well designed, well arranged dispositions, and then you apply external forces, this is classical topic of optomechanics, and you stretch them, and you can play on the interaction that happens between particles that in one direction they become far, and in another one become very close. So, working on this and selecting the right polarization to excite this mode, that extinction curve can change, and you can increase the effect that happens on the nanoparticle arrangement. And you can say what you can do with them. For example, taking a look with a thermometric system, you can observe that increasing the extinction automatically also the temperature increase according to this equation that show you that the quantity of the flux is directly related to the difference of temperature and this terms is related to the extinction that in this case matches the absorption. So the imaginary part of the absorption coefficient itself that again is related to this terms where you are increasing in such a way you are modifying the environment, you are modifying the values of the extinction itself. So, and increasing the section, you get a temperature that is step by step more higher. But in this way, you get only a temperature that increases itself by having the extraction. So, different arrangement shows that you can pull down and again increase the temperature according to the structure that is applied to the system, but in a certain for a certain condition you can also get a cooling effect. Or furthermore, you can modify locally just one of these the position of one particle with respect to another one, you can start to get a modification in the spectrum. So, this modification, for example, the 27% of stretching without the width defect, this is for the fact of destruction. The temperature is not so different at the wavelength that match more or less this part of the system. But when you go here and the not defected structure doesn't have this part here, it is for the defected one there is the defect to your scope. Then it was like a game to find the best disposition of this is a nanoparticle, but realizing nanoparticle, mobilizing them in a structure is not so easy, it's not very simple to do it. Lithographic technique allows to do this now. So just playing with some different shades, we got a structure that matches a large broad insulation experiment, the large broad spectrum for absorption, and taking a look with some different techniques. These optical techniques, there is a confocal microscope, there is a small microscope, so you take a look to the structure with a tip that excites these modes and you collect the signal. It's very nice because you can see where there is a signal that is absorbed and where there is a overlap of this signal. It is the dipoles, giant dipoles created by these structures that are like flowers. And there is a 3D of that one, of course. This remarks the electric field distribution that automatically, this numerical one, you can see in terminal 1 some hotspots localized according to the particle, to the disk that are interacting with each other. And then we characterized this system. It was in an area of more or less a couple of 100 miles or 100 miles, so we utilized the beam, we did the experimental measurements, and we saw that these structures are very good to reach high temperature with not so high intensity or power of the laser, and is almost stable for a time close to a minute. And then, when immediately we shut off the laser, it goes immediately down close to the ambient temperature. So, sounds true that we started with nanoparticles, we tried to arrange them according to their spectral properties in different shapes. We used a disk. We got a temperature that is high, but not okay. But this is what I say that I'm very proud to show you these results, because instead of working with this system that needs some high hard manufacturing techniques that cost a lot, not in terms of money, but time, and especially to find the right recipe, the right arrangements. I started to study how to generate them high temperatures using a combination of metallic, insulator metallic, or electric instead of insulator materials, arranged accordingly to an effective beam theory that is normally commonly used to describe the effect of nanomaterials. As you know, nanomaterials now is very well known in different research fields, are used thanks to their possibility to modify their shapes, their properties according to our scope, and they are not natural materials, but they are human-made materials. So you can arrange them as you want. So, if we use just a combination of these materials where we have a substrate, titanium layer, then we will see, especially because we need this titanium layer, the silver and the zinc and the electric, you got an absorbance, a spectrum that is close to zero. So it doesn't absorb. If you start to make it like a Fabry-Perot, you start to get these absorbance according to varying the thickness of the electric constant or the electric cavity. You can get different wavelength where it interacts. But as you can see, it's not a continuum layer, because the last zinc oxide layer helps to get multiple effects from the better matching for the coming wavelength. So we get a continuous band that allows to design a material that can absorb different wavelengths as you want, just changing one parameter of your system. So simple to manufacture, because you can use very simple techniques like spatterings or the elaboration to design them and fabricate them and get results that it's very interesting. We will see why it's interesting. Because if you consider that this system are mainly made by a metallic layer that is repeated 2 times, so what you expect is a mirror. But you start to open a window where these materials transmit more or less than 50%. And thanks to the titanium layer that was, if you take out just the titanium plus silver alone, you get an absorbance that is flat. When you put on the titanium that is here, the part one, and the silver, zinc oxide, then you close again with the titanium and the cast zinc oxide on top, you get this particular shape. It is a resonance of a fabric objects with this thin layer. You can fit it and you can see that it is a perfect Fanon resonance in this case. That presents one of the interesting features. You can excite this mode more or less at any angle of incidence. It's completely flat. And if you take a look at the electric field confined in this structure, so you are coming from here with air, then the glass, the substrate, you go through the structure and then go out in air, so you can see where we are. The light that is coming is completely reflected up to the wavelength that is matched with this one. Then it passes and it resonates in the cavity, and then is reflected back. So what you get is a structure that is partially transparent, and it reflects in the opposite color, of course. This is normal for these materials. But with this particularity that still remains transparent. And then, this is just to see again that if you do the structure without the thin layer, the titanium layer doesn't got a structure that reaches an absorption higher than zero fabric, and the absorption is here, you get only reflectance, and there's only transmittance, and the reflectance goes down to zero. If you take a look to the metal insulator on glass, the same structure before, but without the cavity, and the titanium, you get something that is reflecting back light. And here is just a better view of the fact that the titanium is mainly flat at every wavelength. The other important things that I would show you is that this kind of structure is illuminated with light, as I did before with the flowers or the nanoparticles. But the flowers is the one that we have experienced, so it's the one that we can use as a comparison. A simple structure made by layers and using powers that are close to the previous one, so that, for example, 20 millimeter square, 75 millimeter square, so there we focalized the beam, so the power was very, very high. If you consider that we focalized it in a structure that is 100 micrometers times 100 micrometers. Here the structure was completely illuminated in here it was millimeter times millimeter square. So the effect is incredible. You can reach 550 degrees in a time that is a fraction of minutes, of course, it's 10 seconds to reach the plateau using the maximum of this power. This is the simulation, of course, that is completely flat. Here it's flat, and the rise up is immediate, but it's a mega simulation. Makes sense for that. And comparing with the fact that here is the behavior in terms of temperature using the same power at different times, taking a look to different combination of materials, the metal is not the metal itself, so the cavity without the titanium layers here, when we do the same system with titanium, we go here. So more than 100 degrees, just thanks to 5 nanometers of titanium layer present below the cavity. And just to test it, the temperature that we reach is not set up to do something. For example, here we place the materials on a cube of ice, then we started to relight it. It reached, of course, not 550 degrees, we have a mass load at 0 degrees on the back, so you need more time, but we don't want to see if we change that temperature, just to see that we start to do the icing effect. Of course, happen with the high temperature here. In this case, you don't need to reach higher temperature as before, because 120 degrees is more than enough for a tissue reaction, for example. And this can be used for such small conditions. Okay, it's time to put down about reducing temperature, increasing temperature. Now we can talk about passive cooling. For me is part of the research that I made here in Florence. So this is part of the tribute to the year. This is a classical situation that you can see if you take a look outside using a thermal camera, and you see something that is more or less at one temperature, that is emitting thermal radiation everywhere, and then, for example, this gas probably uses air conditioning inside, so there is more cold in this part, instead here there is engine and other parts. Why is it important? Considering cooling, okay, for people that works on these research activities, it's very productive because there is a lot of interest and you can publish a lot, but this is another story. The interesting story is that physics helps us to reject part of the thermal heating that we can get from the sun on the Earth, and then the heating produced by the structure itself can be split out to the outer space. And this system was very interesting because a lot of work and possible solution for buildings, for cloth, for greenhouses, photovoltaic panels, because as you know probably, if you warm up photovoltaic panels, they produce aging, very fast aging, and find a solution in that way can help to preserve the photovoltaic panels, or this is a bit of absurdity because using them to store food outside, probably not. But the interesting things happens when you think about buildings. Instead of having a precise temperature control inside, you can manage yourself to use other sources to warm up or cool down. The idea is to use this kind of materials, now we will see how they are made, to cool down spontaneously some situation. Of course, there is the overheat problems. It's another problem. One by one, we'll see. And this topic takes a lot of interest, not only in the research field for science, but also by the European community that a couple of years is sponsoring projects that can use this technology to find possible solution. Because the amount of power used by each of these countries for only air conditioning in 2050 is the hypothesis is that it will increase a lot. It will increase a lot, we will need a lot of energy just to cool down our apartment, our buildings. And this is related to the effect of hot island that they started to characterize that in 2019. The city center of Milan, Paris is heating up, and the previous climate was here, and now we are redshifting it against hot temperatures. So it's a big problem, as you know, and we are seeing the effect of this story. Passive cooling, of course, was well sponsored also in the sustainability that encouraged people to work on this field, to save the planet, and it meets all of the sustainable development goals. So But let's start again with science. And so we will go fast on this part, but the main topic that we need to know for fast relative cooling is if you have the building rooftop covered by black paint, the light of the sunlight is absorbed, the part of the temperature is propagated inside, but also the heating that is produced by this structure is not going out. It produces a radiation that in such a way contributes to the temperature that we have around. If just the rooftop is white, not a high white, just white, it's studied that the reflection goes to 80%, the amount of light that we put out as a radiation, thermal radiation, decreases, and also there is the part of temperature go inside the structure itself. And this is not completely new as a story. It started a couple of years ago, and this is taking step by step more importance. And the physical principle that show how it works is related to the fact that we need to reflect as much as possible the sunlight, and then the body itself starts to use this thermal radiation. This thermal radiation we want to spread out to outer space, but we can do it only in, this is our atmospheric, the spectre of our atmosphere. Our atmosphere, some here, somewhere, has some peaks, and here it's possible to spread out this temperature directly to the outer space. So we can exploit these materials to have a maximum emissivity. Here is this range that is going from 80 to 13 nanometer. And this is expected. As you can see, designing a material like that is possible to have a material under the sunlight that in the thermometric measurement looks colder than the environment around the structure. And it works because, as I said to you, this part of the spectrum is completely transparent, so the light, the thermal radiation can pass through the atmosphere and go directly to the space. So for a relative process, we can go in equilibrium with the outer space. That is very important. And just to prove that the thermal radiation, some materials are transparent, as you can see when you take a look at the thermometric camera, you see through the balloon. Because it's a polyethylene and it is transparent in such a way. As I said, it's not a very new story. This in Florence, and this is ice pyramid. This was built to store ice for summer, and this is an Persian structure that was made the same way, exploring some condition that water radiates to the space, cool down, and then use the flow to refresh the air inside this structure. Online, looking at the aqua. And another test that shows that it's not a trick is when you go on the very early morning and see outside in a winter day, the part of the grass that look at the sky, see the outer space and go down freezing, while the part that is directly covered by to look up directly the sky remains not freezing. Of course, this is a topic also for material scientists because it's a design of materials that needs to select specific spaces, chemical spaces, chemical ligands that are properties that match high emissivity, so high absorbance, in the 80-30 nanometer, and you can arrange different materials to find the right way. So I will go ahead just to show you nice things that we made here in Florence. This is a measure the ambient temperature. This is important because you want to measure the performance of new materials. If you are looking, for example, that if it's able to cool down the temperature below the ambient temperature, you know to measure correctly the ambient temperature, of course. I can assure you that measuring the temperature below ambient is not easy at all, because you are completely surrounded by ambient temperature. It's not it's okay for sure. And yeah, there is the optimal properties of these kind of materials that we made here in Florence. They are highly effective and highly see this part of the spectrum. And they are all kind of materials, probably also too long. All the effect that we studied is related to different properties, but as you can see, it's different. It's very hard to go down ambient temperature during the midday. Normally, you go down a bit during the other part of the day. And just to conclude, we have here can be made with different techniques. This is not for lab, but also for industrial scope. That is possible to make structure that is larger. So we are very close to cover houses, to cover greenhouses that are needed to realize something that can happen in such a way. And also in terms of almost neither with rolling system. And yes, we are close now to time LoT, maybe not. Sorry. So just to conclude, why I talked about these things today is because it's nice to see that using just light, you can get some few possibility to increase the temperature by using a bar, because we're using multi-layers, or you can use different tricks to get a system able to cool down spontaneously some system that can be covered of such materials. And yes, thank you for your attention. Is there a question? So this is important, of course, because normally the first time is that was being done is using an effective layer and then an emitter. Because this way, if you use a mirror, a very good mirror, silver, a thick layer of silver, you can reflect part of the light. You have a compromise because it absorbs a bit of UV, but you can compensate as a trade-off with the light that is reflected. Then you need to put a polymer, maybe a polymer, that match with one ligand this band, because in this way you get the selective emissivity in the transparent layer. Different tests that this is made by a colleague of Lens, this is numerical, but then we made experience also that you may use two different systems. An emitter and then on top a material that allows infrared to pass through, of course, if you want to split out, and a diffuser, so a material that contains micropores or scattering medium in such a way that allows to reflect light that is coming from the sun. And then, of course, only one solution means you mix everything, so you get a material that has pores, nano perturbations, so all the things that are for the visible spectrum, so smaller enough to diffuse, to scatter the sunlight, and then the other chromatic matrix, the arrangement made by, again, one couple of materials that stay on this part of is an example of making a system like that. We made a paint with a lot of scattered glass bubbles that are particular kind of bubbles made by freehand, that is a core glass, again, that is like a sphere, in a paint, and then we cover with this nanoporous polyethylene film that allows to reflect the UV, increase the emitted infrared heat. So this is like a combination of more or less only one material. That, as you can see, it reflects a lot of the sunlight, and it has the paint with everything is broadband everywhere, while only the film is not so much higher, but it has some peaks and taps. No other question?
Is there any question? Okay.
Thank you.
primary platform for micro laser and spectral encoding. So the general idea is that the soft primary platforms are plenty and versatile for many applications involving photonic. The thought will be divided into main parts. The first part indeed related to spectral encoders and in particular optical filter for reconstructive spectroscopy approach and microspectrometer, and the second part more devoted to active devices. So in particular polymeric material for micro laser, photonics, and means, okay. So, but let me start from microspectrometry. You know that miniaturized devices are of tremendous interest for many applications, from industrial quality control, environmental monitoring, agricultural control, so many things that involve field analysis and accurate measurement. So, for this kind of application, you need compact devices but maintaining high resolution, high spectral resolution. And with standard kind of approaches, in particular involving diffraction and dispersion, things are quite challenging. So you know that there are many kinds of microspectrometer based on reflection and diffraction, transmission, diffraction, breaking, but also more exotic kinds of concepts based on waveguide dispersion. Okay, so imagine a miniaturized device where you exploit the dispersion of the waveguide. So many waveguides of different length can separate aspects. Okay, so it kind of really has no spectrometer. But if you think to all these devices, you need optical path length that are long. So longer is the path length, more high is the resolution, the spectral resolution. So think, for example, to standard benchtop spectrophotometer, they need long and large photons in optics in order to preserve a high resolution. So to miniaturize devices with this kind of concept is tricky, but there are beautiful examples also of miniaturized device based on fractional optics. For example, the quant. Here we have concave grating that at the same time it's two things. One is to separate the spectral component, and the other one focuses in different positions. So without the addition of other collimation optics, you can have devices that are really compact. Compact, when I say compact, I mean footprint of a few centimeters with a resolution which is also below 10 nanometers. Okay. Of course, there are kind of problem in miniaturization related, for example, to etching-induced scattering losses that degrades resolution. Okay. So there are also nice examples based on Fresnel lenses that are lightweight and very low cost. There are some kind of application also connected to smartphones. So this device can be really versatile and compact, but again, here the resolution is related to the optical path. Okay, so researcher starts to consider something a little bit different, trying to overcome this problem of the path length, and indeed to overcome the problem of the path length in order to enhance resolution. Okay, so there are beautiful examples of Fabry-Perot and array, narrow filter array, broadband filter array, so many things, also up to photonic crystal and metal surfaces. So think to these devices as optical encoder. Their spectral transfer function can be also really complex, but if you perform recalibration of the spectral encoder with a high resolution, and then you rely in part of the reconstruction on a post-processing algorithm, it is possible to retrieve with very high spectral resolution many analyses. Okay, so the very clear example reliable and also very compact. Think, for example, to the fabricator that before Giuseppe introduced, it can be a really compact device. For example, a single optical encoders where this fabricator resonator which the mirror can be changed. Okay, so the distance among the mirror can be varied, for example, in time. So these devices can itself be a very high resolution spectrometer. So by changing the distances among the mirror, it's possible to tune finally the resonance of the wave transmitted, and so it's possible to scan a spectrum. Once that you know your the slip in length, you can retrieve your spectrum. Okay? A very similar idea is also based on Bragg reflector. In that case, complicated Bragg reflector based they need a lot of layer of alternative materials, so fabrication is not so easy. But in this case, you can extract, for example, the difference in the angle of incidence, okay, and you obtain each time a different stop band that is centered at a different central wavelength. So again, you can tune your spectral encoders at different wavelengths. But the very clear example that you can imagine is that one. So imagine a 2D array of narrowband optical filters. So ideal delta function filter. Think after about the complexity of the fabrication of the system. So in this case, spectral reconstruction can be really easy because it's very easy to have this kind of array on the top of a CMOS array. In that case, simply the final spectrum can be the pixel, okay, associated to the intensity, by knowing exactly the central wavelength of all these filters. So post-processing algorithm, it's really easy, okay? Well, but in this case of this narrowband filter, things a little bit. If you want larger bandwidth and you want high resolution, you need a precise sampling of the spectrum. So you need lots and lots of filters. Well, so researchers have to think again to something also to overcome, for example, the number of optical encoders. And they start to think to the most exotic kind of transfer function, for example, disordered material, but even a multimodal fiber can act as a microspectrometer, because the spectral pattern of a multimodal fiber is very sensitive to wavelength variation. So, if with a tunable laser you characterize this spectral pattern very finely, then with the help of a post-processing algorithm, you can reconstruct your announcing. Okay? So also nice examples are based on non-ideal broadband optical filters. So when we have a broadband optical filters, now it's not anymore the delta function that you can immediately relate that pixel to that wavelength. So things can be quite particular, but the nice thing is that with few filters element, by knowing very well their calibration, so their spectral response over the bandwidth of interest, it's possible with few intensity measurements. So you really need few pixel, few filters, few measurements of intensity to reconstruct an announcement. Okay? So this is precisely the concept behind reconstructive spectroscopy. Half of the measurement is based indeed on the optical elements. Okay, so these few tens of integrated intensity. The other half relates and is based on the post-processing algorithm. Okay, this is precisely what we are looking for. So we are measuring 25 elements for our 25 filter array. Suppose we know very well the precalibration, the transfer function of this filter, and so we are looking to our spectrum reconstruction, to our spectrum methods of calibrated transmitters, and so our unknown signal, so the unknown spectral components, they are LoT. So this is an equals problem, so an underdetermined problem where you have a few known intensity and a lot of spectral component to retrieve. Okay, so we can do this relying on convex optimization algorithm. It's for this reason that when I talk about half and half is the measurement, but half also rely on the robustness of the post-processing. Okay, and with this kind of approaches, it's possible to retrieve with very high resolution many kinds of spectrum. Okay, this is precisely what we are doing now in the lab in collaboration with Zeiss company in Germany and with KIT. We have really no idea, smooth transfer function of dielectric filter, and when I talk about dielectric filter, think to totally non-idea gravity. So few layers of polymeric material of alternating refractive few layers are 2-3 layers. Okay, with these 2-3 layers we can cover 300 nanometer bandwidth. So look at these transfer functions. They are really smooth. They are very good then. But with the help of a good algorithm based on convex optimization and a good spectral calibration, you can reconstruct a large variety of spectra, from halogen lamp and broadband spectra up to silver, narrowband filter spectra. So many kinds of spectrum with a resolution which is below 8 nanometer. And this device and this design is really common. Okay. So we also move to another kind. This is just an example. This is another one. So think to the large variability and diversity that polymeric soft material offer in terms of realization of cheap and very easy filter. Okay. So in that case, we are working with cholesteric liquid crystalline network. Many of you maybe already know about liquid crystal, which is a phase between a solid and a liquid. You know that at room temperature, some kind of liquid crystal exhibit order structure. Chiral liquid crystalline are particularly nice since they exhibit this chirality. Okay. Well, so it depends on the pitch of the helix that they can form, that they offer different reflection band. We can call them stop band for a certain circular polarization. Okay, for example, a circular polarization of the same emissive of the crystal can, for the right wavelength, experience a total 100% reflection. Okay, when we have light which is like in our case is 50 unpolarized, we have a stop band of the 50%. Okay, but it's very nice that we can relate with each of the helix to the central position of this reflection band, and the birefringence is related to the band. Okay. Well, with this kind of chiral compound and a different concentration in polymeric network, we create a lot of different kinds of cholesteric liquid crystal-based filters, and so it was very easy and nice in this case to reconstruct also ultra narrowband transfer functions, like in this case, laser-like features and still broadband. Okay. Again, relying on a good post-processing algorithm that involve complex optimization and regularization. Okay. Now, I'm not going too much into detail, but of course, I know many questions for this. Maybe now it's good to switch to the other part, even involving now again polymeric material, but now considering active doping based on organic light harvesting complexes. Okay, so in particular. is called radiosplitting. Okay, this kind of energy separation, this value, is really proportional to the coupling, okay, on the photonic mode and the material transition. Okay, so why study organic polariton feature with organic material? Organic material are very nice. I know I like a lot easy application. So the device now maybe something. My time that is okay. 10 minutes. Okay. Well, there are plenty of electronic transitions, so they offer a large tunability, and so easy of applications, as I said before. So many things, and in particular for polariton photonics, is very important the fact that organic molecules and aggregate offer large exciton binding energies, and this allows to observe polariton features even at room temperature. And from the other side, the fact that they have so large big dipole moment, we can relax indeed the complexity of the fabrication process. Okay, and we can observe strong coupling phenomena more easily. Okay, so there is plenty of demonstration from ultra threshold polariton laser up to the fact that strong coupling inside microcavity has observed to increase some chemical reactivity, but also to enhance energy transfer, for example, mechanism, and also beautiful example of logic based on polariton for optical computing. So many things, okay? The study that now we are doing in our lab is based on diode polymeric material. In particular, this dye is a high-fluorescent small molecule laser dye, so LoT. It is a very benchmark system, but it is a small molecule. So here the fabrication process was intentionally very simple. So we want to study the trade-off among reaching a large strong coupling while maintaining good photoluminescence efficiency from our microcavity. Okay, so we start from a very basic design on using transfer matrix method in order to match the photonic mode with the material resonant transition. Now I will show you. And as I said before, fabrication was very simple, involving silver deposition via physical vapor depositions, and then the part of the dye. So the dye block layer were substantially developed using web processing, so spin coating in particular. Okay, so here there is the phases of our diode in CG when it is in an alcoholic solution, so for example ethanol. When we try to create a very slim field, very thin field with high diode doping concentration, things are quite different. So we observe some kind of aggregation. In particular, look at the high energy shoulder on the absorbance of the field. Okay, this is quite important for our explanation of strong coupling. Here there is an angular result transmittance map showing how our exciton behavior doesn't depend on the okay. Here there is a characterization of the microcavity embedding the bare polymeric material without any kind of active doping, so showing the standard classical, you can say, mode description with it. Okay, so what happens when we embed LoT in CG? Inside our cavity. So you look here on the left the bare cavity. When the dye, it has proper dye concentration, I'll show you after, is embedded inside our polymeric field. We see the opening of beautiful polariton branches. Here there is a scheme, it's very simple. We modeled with a generated system. And here is LoT again. Well, look, our splitting, which is proportional to the coupling constant G, is our important point. So here we perform a large statistics source for so many dye concentration and also many different kind of communication approach. But here just simply focusing on the concentration part, we start to see for a concentration doubling of 8%, so 8% of rodents over the polymer mass. Okay, so we see the starting of the lab splitting, the rising of the lab split at so low concentration, and this rapid splitting increased for high concentration upward to 200 millielectron. Okay, this is a very large number for a small molecule that is not a larger average. Okay, well, our results also are in a very good accordance with the theoretical model. This is not a fit. This is exactly the theoretical model where there are inserted the parameter of the dye. Okay, this is not a fit. So the accordance is quite good. For high concentration, it seems that we incur in some kinds of plateau. This is of course more related to the fact that larger and important part of algorithms start to rise, especially to high energy. From our cavity we also study photoluminescence emission. This is quite important. We want a large strong coupling, but we also want to preserve photoluminescence efficiency. We pump our system above the lower clariton branches using a CW laser, and we observe efficient recombination from the lower clariton branches for a certain kind of range of concentration. Here there are the interior limit up to 50%. Okay. Well, of course there is a trade-off, as I said before, because increasing too much the concentration will inevitably in concentration. Okay, so there is a trade-off among these two things, so large strong coupling and high photoluminescence efficiency. Okay, so here I simply recap these beautiful results based on small molecule laser molecules that experience some kind of aggregation due to the high concentration doubling, but also discrete causing processes. This is a very important result toward the realization of ultra-threshold devices, light sources in particular, micro laser but not only. And this is part of a bigger project. This is a preliminary project, a preliminary study inside a bigger project, which is a European project involving many European partners that are focused on the realization of a solar pump devices, which is based on another kind of activity. Okay, so the novelty stays in the components of this activity. In particular, many of you will know about photosynthetic antenna system that are attached to some kind of photosynthetic bacteria that lives in the deep, you can say, of the ocean. They receive few flows per hour, so they are trained by the evolution to absorb a lot of light and efficiently find a specific location for the life of the bacteria. So these antennae are based on hierarchical architecture of chlorophyll molecules, and these are going to be our pumping system for our laser mirror. So think to the organisms that you see before. So we are going to do something similar, so combining this nanoscopic antenna system to optimize the rodents is one of these examples. Here in Florence we are developing the micro-corrective system, so the micro laser. And so here there is zooming in the natural antennas, but also the artificial. Okay, so we are also studying artificial antenna systems that are inspired by the natural ones. So in particular on the right we are looking to a nanotube of cyanide dyes, again a laser dye, that in water creates beautiful nanotubular architecture. And both these systems has so large excitonic peak that can couple easily with solar radiation. And so this is the ambitious way of the Apache team. So going to the final part of my talk, I want to thank a lot all the people and my collaborators, the people of my team, and all of my collaborators. Yes. Thank you very much.
So, I'd like to leave us 30 minutes left. Because it took a shot. No. Okay, so thanks a lot for the invitation. It's really an honor to be here. And I will try to give you some idea of studies that we are doing with ultra-photon between Florence and Pisa. Actually, my group is split between Florence and Pisa. As you see from the title here, we want to study the supersonic phasor matter. This is a new phasor matter that was conceived only theoretically until recently. And the idea of the supersonic is a phasor matter, a quantum phasor matter that has properties both of a superfluid and of a solid. You probably know how a crystal works. In the crystal you have isolated atoms. Here, each of these wave functions represents one atom, and each atom has a separate wave function for the neighboring one. And the isolation, the localization of the atoms in the crystal gives rise to all the properties that we know of the solids, the stiffness, the plasticity, and so on. On the other completely different side, there are superfluids. In superfluids, the atoms are fully delocalized. You cannot tell where a single atom is. And all the atoms share a single macroscopic wave function. So this is typically Bose-Einstein condensate is normally a superfluid. And these two phases of matter are completely different. Superfluids are liquids, they flow, they have a particular quantum properties, and they have nothing to do one with each other. Many years ago, there was a proposal for a phasor matter, a supersolid, which would combine both properties. So the simple idea in this case is that you have a macroscopic wave function, like here. So all the atoms are delocalized, you cannot tell where the single atom is, but still there is a periodic modulation of the density, like in a solid. The only difference is that you see here the wave function does not go to zero, or the density, the wave function square, does not go to zero, which means that you have a single wave function. So the atoms are completely delocalized here and there. And this, so this is very easy to draw here. I simply make a wave function as I want. But the question is it real? Is there a physical system where this ideal concept can live? And many years ago, there was a bunch of theorists, you see, starting from Eugene Gross, 1957, then around the age, so I was born more or less here, so many years ago, there were all this group of theorists studying theoretically the possible properties of this supersolid. Here, one notable example is Anthony Leggett, who unfortunately passed away recently, who is one of the giants in the theory of superfluids. And so the idea was, well, can one find this material which has both the properties of crystal and of a superfluid? And for many decades, the international community was studying the typical superfluid. If you ask you what material is a superfluid, many of you would answer liquid helium. Liquid helium at low temperature is a superfluid. This is the traditional superfluid. And so the idea was to take liquid helium and then put it under pressure until it becomes a solid. So if you take liquid helium at low temperature, below 1 Kelvin, then you compress it, then you will get a solid helium, and the idea would be that here there could be a supersolid phase, perhaps. The supersolid phase in the helium would arise from the fact that each atom, so this is a lattice of helium atoms in the solid. If you have some hole, some vacancy, then since helium is quite light, so the wave function is quite broad due to the zero-point motion, you could have some motion of these vacancies. They are bosonic, and so you would have a mobile bosonic system with a periodic structure, which would represent a supersolid. And for many decades, my colleagues in this field were looking for this phase. Some 10 years ago, some 20 years ago, there was the announcement that they found the supersolid phase in helium, but then soon they realized that there was another effect, a completely different effect, and so there was some depression in the international community because it seemed that this supersolid phase was not existing. Then there were ideas to go over the problem of these. There were proposals for studying not a system like helium, where you have these vacancy supersolids, but to take systems where you have many particles in each lattice side. There were these proposals for studying systems with soft core interactions, where you could have a periodic structure in the wave function. So this is again a map of the density. This is a computation from some years ago, 30 years ago, and the idea would be that you could have a supersolid but with many particles per lattice side. This is what now is called a cluster supersolid. So again, this was all theory and many experimental attempts. When finally, 50 years ago, we found an interesting system, which is the type of system that I'm working with. You probably saw a lab in Lens, and you will see another one in Pisa. The idea is to work with atomic superfluids, so a gas of atoms at very low temperature. They realize as a condensate, which is a superfluid. And if you take strongly dipolar atoms, you will see we work with dysprosium atoms, which have very strong magnetic dipole-dipole interaction. Then you could exactly find the condition to realize one of these cluster supersolids. What's the idea is that, well, everything if you want is based on the peculiar interaction between dipoles that dipoles like this, they repel. To dipoles like this, they attract. Right? And then if you take a sample of many of these dipoles in a Bose-Einstein condensate, you might find a situation where the system, which is naturally a superfluid, so a Bose-Einstein condensate of atoms with interactions is naturally a superfluid. But thanks to these special interactions, you might also get a periodic modulation. So let me give you some small idea of how we do this in the lab. You probably saw it. So these are cold atoms. We start, this process is not really a metal. Actually, it's a metal with a very high melting temperature of the order of 1000 Kelvin, so we have to cool it. By laser cooling, first stage goes to 1000 Kelvin to 10 Kelvin, then 10 microkelvin by laser cooling. This is not enough, so we have to continue the cooling with some evaporative cooling, and at the end we use for this an optical trap, and at the end we get a Bose-Einstein condensate with the temperature of the order of 10 nanokelvin. So this simple story, as you probably know, took many years in the international community to realize with several Nobel laureates on the way. But my generation had the luck to find all these techniques ready, and so we have these systems in the lab. These are some pictures of the atoms. We work with dispersive atoms. This is a picture of the transition to Bose-Einstein condensation, and then this is our small supersolid. It has something like 50,000 atoms at low temperature, and this system has a macroscopic wave function and all the Bose-Einstein condensates. So this is a superfluid exactly because all these atoms have this single macroscopic wave function. So all the atoms are localized, single macroscopic wave function with modulus and phase as a standard superfluid. So this is standard superfluid known since 30 years now. The discovery actually was motivated by the theoretical proposal by some colleagues some years ago, and the idea is that thanks to this anisotropic dipole-dipole interaction, and in particular to the existence of an attractive part of the dipole-dipole interaction, when you have two dipoles sitting one on top of the other one could get a situation where the excitation spectrum of the system develops this Rotonic minimum. Essentially what I'm quoting here is just take a condensate, you imagine to create a sinusoidal modulation with some wavelength that moves with some velocity, and here I'm quoting simply the kinetic energy as a function of the wave vector, 2 pi over now. Normally, for a standard liquid or a standard superfluid, you would expect to have an almost linear situation like this. This would represent phonons or sound waves. Here, thanks to the attraction in the dipole-dipole interaction, you would create this minimum. And when this minimum touches, if this minimum touches 0, you would expect to create with 0 energy a modulation with some wave vector and 0 velocity. So if you want, this corresponds to a standing wave, in the density of the system, like in a crystal. And this could be created spontaneously if the energy touches 0. So this was the theoretical proposal many years ago. There were some very interesting experimental works done in Innsbruck, where they observed indeed this Rotonic minimum, or in Stuttgart, where they observed that indeed a crystal type of structure was developing in these dipole condensates. interactions, there are actually a series of two different quantum phase transitions that go from a standard superfluid to a crystal type of a system with a periodic modulation and individual clusters, passing through a region where one has exactly all the conditions to realize a supersonic. So, a macroscopic wave function, like here, but with a periodic modulation, like in the crystal. The evidence of this, what I'm showing now, is the first measurement that we got of this new phasor matter in 2019. This was made in Pisa. This is the one of the labs that you will visit, I guess, on Monday. And here we were looking at the Fourier transform of the density, and we could see that we were passing from a standard Gaussian condensate to a system which has a pattern in the density that resembles the one of a two-slit interferometer or two-slit system. Here you can see better the density in the supersolid phase as a modulation, and since this is the Fourier transform, this is the Fourier transform of the density which has modulation. This implies that also in real space you have a modulation. So this was the first evidence of a supersolid of the supersolid phase. Here we checked that the system was coherent simply by waiting for some time and checking that the phase of this modulation was constant over time. I am showing you this other picture. This is taken from internet. This is something that you can find in the internet. And this is a picture of a ferrofluid. You can find it on Wikipedia. The ferrofluid is the classical analog of the supersolid. This is the classical liquid, so not the superfluid, in which there are magnetic particles dispersed. So it's a suspension of some magnetic particles in a liquid. And in the presence of a magnetic field, here there is a magnet below, the system develops this periodic modulation of the density. So this is a classical visualization of the supersolid. In the supersolid, the starting point is not a classical fluid, but it's a superfluid. And it's very similar, it's a cluster system, meaning that here there are many particles per each density mass. Let me go rapidly now. We have been studying this type of system, our group and other groups, notably the groups in Innsbruck and Stuttgart. Over the last few years, we have been studying various of the properties of the systems. Here are advanced aspects of quantum physics, such as quantum phase transitions, vortices, fluctuations, and things that you probably know only by the end of your master courses or even during the PhD. So I won't spend much time on this. The very interesting thing that came out, so when we started, around 2018, there was no idea of any experimental system with supersolid properties. During the last few years, you can see here the dates, 2019, 20, 21, and so on. Many other condensed matter systems started showing supersolid-like properties. Essentially here, there is a collection of all the known superfluids. Here there is helium-4, this is a layer of helium-4. This is helium-3, which is also superfluid. There are superconductors. Superconductors, you know, they there is a superfluid of Cooper pairs of electrons. There are the exciton-gravitron condensates, spin condensates in quantum magnets. Many of these systems show also a spontaneous modulation of the density. And so in principle, they are a supersonic. Now, studying these differently from the cold atoms that I showed you, these are very high density systems, very strongly interacting systems. They are not a gas like our cold atom systems. And so, studying these systems both from the experimental point of view and the theoretical point of view is very challenging, and it will probably take many years before our colleagues will have clarified the property of this system. And so we are very happy to use now our cold atom system, which is much simpler, less interacting, easier to reproduce theoretically and to model theoretically, to study the general properties of this phase, which is no longer an exotic or a phase created by the dream of some theorists, but seems to be a very general phase of matter. It seems that many of the superfluid systems or superconducting systems existing in the labs have also a supersonic phase. So this is becoming a very general subject of study in condensed matter. And one of the things that we have been working on recently is to study the so-called superfluid fraction of supersonics. Let me give you just the idea. This little, so here probably some of you at the master level will understand what I'm telling, but let me try to give the idea for everyone. So this is a conceptual picture. Take so let's start from the upper part. Take it's like a superfluid. So normally the superfluid has a constant density. The superfluid is a liquid-like system. So the density of the superfluid is this line here is constant. Now you take the superfluid, you put it in a box, and then this has a macroscopic wave function with a phase, and then just imagine to apply a so-called phase twist. So you make a change of phase from 0 to some value on the other side. And then you ask, what's the minimum energy state for the system? Then what you have to do, you have to remember, so this is the macroscopic wave function with the density and phase, and you have to remember that in this case, in quantum mechanics, the velocity is essentially the gradient of the phase. So it's simple how you calculate the energy. The energy is simply the kinetic energy associated to this quantum mechanical velocity. And this is just the expression of the kinetic energy. So this is essentially 1/2 m times v squared. Is the kinetic energy, of course. So you have so this is so because of this gradient here you have the gradient square, and then you have to minimize it to minimize the energy. No, and so normally what you do you minimize. And you have to average your velocity all over the extension of the system by weighting it with the density. So this is the standard calculation to minimize the kinetic energy. Average over your system. So normally this density is constant, so you can take it out of the integral, and then the result is very, very simple. You find that you minimize the energy by creating a linear gradient of the phase. Linear gradient of the phase means, since the gradient of the phase is the velocity, means that the velocity is constant all over the superfluid. And so the superfluid moves at constant velocity. This is the reason why there is no friction. It's a superfluid. There are quantized vortices, and so on. All the properties of the superfluid is based on the fact that here you can take rho out of the integral. Now, what Leibniz noted already 55 years ago is that if you take a supersolid now, the density is modulated because it has a modulation calculation of the density. And so this changes completely the situation because now we have to minimize the whole integral. And the situation is quite different. What you find is that now the phase, you have the energy not by changing the phase linearly, but by keeping essentially the phase constant when you have much of the density and by varying it when you have low density. And this means now that the velocity is not constant for all the system. Essentially here, the peaks stand still, they do not move, and only this background part where the density is low moves. So it's a completely non-classical behavior. You have, if you want, the combination of the classical system, your crystal part stays still, and the superfluid part moves. But here I'm not speaking correctly because it's a single macroscopic function. And by relating this energy here of the supersolid to the standard energy of a superfluid, like define this superfluid fraction, which is a quantity that should vary between Z1 for a standard superfluid to 0 for a classical solid. And so one of the things that we measured in our lab, we make the story short now, we have been working for 5 years almost to try to measure this quantity because it's the key quantity that defines how the supersolid is different from a standard superfluid or a standard solid. We tried various methods. I have no time to tell you about now. Probably you can ask about this when you go to Pisa to visit the lab, because we measured all of this in Pisa. And we finally found, we tried to build, we are now working to try to build this angular structure as Tony Leggett predicted many years ago. This was hard. What we did, we found a clever way of measuring this quantity, which is to note that this structure here, with peaks and minima in the wave function, is nothing else than the structure of a Josephson junction. Supersolids are essentially Josephson junctions with no external barriers. They are a special type of Josephson junctions. And by simply measuring the tunneling energy of the Josephson junction, it is possible to measure the superfluid fraction. What we did in the lab is to realize one short supersolid like this, with just two big maxima, and to measure the typical Josephson dynamics by looking both at the oscillation of the two peaks and of the phase of the wave function. And from this we could deduce the superfluid fraction. Let me finish with this picture here. This is a measurement of the superfluid fraction that we did. The C goes from 0 to 1 in principle. And along this axis we can change the interactions in our system moving from the superfluid on this side, which is the superfluid fraction consistent with 1. You can see the experimental points. Towards going towards the crystal side, which should have a superfluid fraction 0. So all this region here where the superfluid fraction is between 0 and 1 is supersolid. So this is the demonstration that the supersolid exists, that the theory by Leggett was correct. And if you want, you can think the supersolid is the only physical system which has intrinsically Josephson oscillations, because the supersolid is just a spontaneous array of Josephson junctions. And with this, let me show a picture of the people involved. These are the main people involved in Pisa. In the lab, you meet some of them, and you probably saw some of the people that also here in Florence are building one setup to study this change of topology. So
Because if you make a phase twist, I expect a change of topology here. If I'm not mistaken.
you mean a phase twist of this type?
Yeah.
So a phase twist of this type here.
Yeah.
Well, this phase twist that I'm speaking here, maybe you can, maybe this becomes a bit technical, but this phase twist here if you want. The phase twist is a theoretical concept, not that you take your system and you force a change of phase on one side. Experimentally, what we do phase imprinting. We use a laser beam to imprint the phase profile that we want on our system. And this produces dynamics, not a change of topology. But maybe what you're saying is related to the phase transition also.
No. So about the phase twist. It's only was about the phase twist, so it's okay.
Okay.
Perfect. So thank you again, Giovanni, and the talk of the finished. We finished our marathon for today. It's incredible.
So that's a wrap for today's seminars. Just one little reminder for you to second. Should work. Yes, okay. So just a little reminder to scan for the program if you arrive later, some of you arrive shortly because of transportation. And in the program we also suggested a couple of places you can go to eat tonight if you are really tired and you want to go to bed early. So you don't want to walk around too much. And we also have some side quests if you want to have some fun in the city or the next few days. And Ismail is going to explain all of it. No, I have to explain.
Just explain to our way what to explain. I tell you what also to explain now the messages that were made. So I think only that the game is all. I don't know.
Okay.
That's okay. You can start to play our game. It's called LoT game.
The end prizes will be given to the event of Monday evening. There are some quests in Florence and some other quests in Pisa, so have fun with them.
And also there are side quests with our organizing committee, so please engage your
Each of us designed a little side quest that you can have fun with, everybody with their own flair and with their own interest in mind. So I hope you like it, or if you have any new suggestions for next year.
Well, next year maybe 2 years. I don't know, we don't know. Okay, so now the next part of the program, I suppose that we're going the autos.
So if you need to go to the bathroom or get some water or anything, right now we will collect all your things and we'll go together with the bus to the hotel. The rooms are available now, so you can park out to the hotel if you want to, or do whatever you want in the city if you want to eat somewhere else in the middle of Florence.
And advise, pay attention time to the bus, because I suppose that at midnight there will be no bus.
There's a tram up to 2 a.m., but afterwards you might have to take a plane, so consider that.
Okay, so that's all for today.